So can you see my slides?
Yes, we can see your slides full screen. Do you want to try advancing them just so we can?
Okay, excellent. Thanks a lot for the invitation, and I'm truly sorry not to be able to come in person. So I was really looking forward to this workshop, but unfortunately had to cancel. Okay, so before I start, let me praise my collaborators here listed on the left. So without them, of course, nothing of the material shown would be possible to achieve. Okay, so well, probably I will need to cut it short on the introduction, but let's say the search for the confirmation or the proof of existing extensions of the standard model that are realized in the nature is the main front nowadays in particle physics. And so the standard model is remarkably a good tool that is really very hard to prove wrong, except we know that it is notoriously insufficient. So most of the evidence for that comes from cosmology, so dark matter, dark energy, the matter antimatter asymmetry, but also mathematically and so from particle physics we know the hierarchy problem and the apparent fine-tuning of standard model parameters that so there are many of, well, not too many, but still not just a few. And we do observe some very strong hierarchy among them. And so the searches for possible extensions go along three main frontiers. At high energies, well, we just try to produce the new heavy particles directly. In astrophysics, that in fact has shown to be a very fruitful one, but also the precision frontier at lower energies, where we try to compare very accurate theoretical precisions with equally accurate experimental measurements, and deduce information about beyond the standard model physics from this. Now, the parameters of the standard model comprise charges, masses, and mixing angles. But now the Lagrangian of the standard model operates with quarks and leptons as well. Here, so I will be talking about the precision tests with the hadrons. So now at low energies, quarks are not directly accessible. So how can we access their fundamental properties through the hadronic mass? And the answer is that to do so, you need to look for conserved currents, and so you can test charges associated with these conserved currents. Now, the strong interaction may modify observables only at next to leading order, so not at leading order in the electromagnetic constant. So this already sets the scale to a few parts times 10 to minus 3. But the experimental and pure electroweak radiative correction accuracy lies at 10 to minus 4. So now, in terms of heavy BSM particles, this corresponds to the scale of roughly 50 TeV. And so there is very competitive also with colliders. But obviously, because at low energies the quarks are hidden in the hadrons, the hadronic structure effects play the role of the main limiting factor in many cases. Okay, so here I will be addressing in particular the weak mixing angle and the Cabibbo angle, or VUD. and see how radiative corrections play a role here. Okay, so now the weak mixing angle is certainly a central parameter in the standard model. It describes how the hypercharge and SU2 bosons mix to give us the massless photon, the physical fields, the massless photon and massive Z0. And there are many ways of accessing the weak mixing angle. So because the coupling constant to the fermions of the Z boson depends on the weak mixing angle, you can measure molar scattering, so purely elliptonic. You can produce the Z that at colliders, where then it will decay into quark anti-quark. But also you can access it at lower energies with atomic systems, with coherent neutrino scattering, with parity violating electron scattering elastically or inelastically, and also with the inelastic neutrino scattering. So now the radiative corrections are certainly present and modify the value of the mixing angle depending on the kinematics at which it is accessed. And so here the running in the standard model is shown on this plot. So you see that clearly measuring it at the Z pole and at low energies will give you different results. And it is this running, the clean prediction of the standard model, if there were nothing else in nature, is what we want to test. Now, beyond the sensitivity to heavy BSM physics, as I mentioned already, up to 50 TeV, given the precision of the planned experiments. Also, here we will be sensitive to light dark gauge sector, and here because of the scales at which the experiments will run, we will be sensitive to these light mediators, where the masses above 70 MeV are still not excluded. And here, this really very well illustrates the complementarity to collider searches, which where of course you will not be sensitive at all to any light new physics. Okay, so now how do you measure the weak mixing angle at low energies? So you can, for instance, scatter polarized, longitudinally polarized electrons of unpolarized nuclear or nucleon target. And if you go to very low momentum transfer, then such a parity violating asymmetry, after you factorize out the couplings, will be directly proportional to the weak charge, so which is just the point-like coupling of the Z to whatever the target is, times 1 plus correction term delta. Now, this here is the relation of the weak charge to the sine squared theta, so the weak mixing angle. And it is remarkable that for the proton, the weak charge is just accidentally suppressed. So it is only 0.07 roughly in the standard model. So now Q-weak measured this parity violating asymmetry at low Q squared, 0.03 GeV squared, and extracted it to relative 6% precision. That gave a Nature publication back in 2018. Now at Mesa, there are in Mainz, there are plans to go down by an order of magnitude in Q squared and improve the measurement precision to 1.5–2%. So which is would really be a breakthrough. So now at this precision, one needs to include the the one loop standard model radiative corrections, and this has been done back in the 80s by Marciano and Sirlin. Now, apart from these radiative corrections, so now let me explain a little bit. So this part here represent the running. So these are universal corrections, but the boxes are non-universal, and so those need to be evaluated for each process separately. Another correction that is process specific is this delta, and that encodes hadronic structures such as the size, so the charge, and well, let's say in this case it's the neutron skin, spin, strangeness, and so on. But the nice thing about it is that it is suppressed at low Q squared. So therefore, that's why one of the reasons why Mesa wants to go to such a low Q squared. Also, the energy dependence of this correction is trivial in the sense that it's purely kinematic, so it is known. Instead, the non-universal radiative corrections, such as boxes, have non-trivial energy dependence, and also are not suppressed by Q squared. So the suppression is in alpha or pi, so which is roughly 10⁻�3. That of course sets the scale of the needed precision in this formal way just to some 10%, which is in general very much feasible. Okay, now turning to the beta decays. Well, so if the weak interaction were exactly universal, one would expect that the rates for muon, pion, and neutron decays would be exactly the same. Well, modulo phase space. Now, the rates are close indeed, which at the end led to postulating the new force of the nature, so the weak interaction. But they are not the same. And so the solution to this discrepancy was the introduction of quark mixing matrix, Kabibo, Kobayashi, Masukawa, and inclusion of full set of radiative corrections. So all of these ingredients, including radiative corrections, by the way, are crucial ingredients for the establishing the standard model as a precision tool. So now, although instead of just comparing one single number, now through quark mixing, it is so the universality of weak interaction becomes somewhat more intricate, but still the unitarity of CKM matrix is an exact and model independent constraint that measures the completeness of the standard model. So in particular, the most well-known constraint on the unitarity comes from the upper, from the top row of CKM matrix, and requires the squared elements to sum up to unity exactly. Now, the element VUB, the rightmost, is very small, so that VUB squared is at the level of 10⁻⁵ and can be neglected at the current level of precision. And so one can describe the unitarity relation in terms of just a single mixing angle, the Cabibbo angle, theta c, so that VUD is its cosine and VUS is sine. So now combining data on nuclear and nucleon beta decays and kaon beta decays, one obtains nowadays a 3 sigma discrepancy with the CKM unitarity. And the reason for that is a re-evaluation of a single radiative correction of the standard model, the gamma W box. And it is also the VUD that has shifted. So here on the right, you can see how the 2018 value was shifted to the left, and you also see that the uncertainty was reduced. Now, the BSM searches at low energies versus collider are and will still become will still remain very relevant and competitive even in the new LHC era. So here you see a summary of the weak mixing angle measurements at colliders, but also here below the future measurements at MESA in Mainz and the Muller experiment at JLab. Now, the same is true also for beta decays. So because they constrain very effectively the non-standard scalar tensor charge current interaction. Here, the comparison is between the beta decays and existing bounds from the LHC. So you see also that they probe very different directions in this parameter space. Now, projecting it to the future more precise measurements of beta decays will still remain very competitive and relevant even in the high luminosity era of the LHC. Okay, so now let me move on to describing how the Electroweak boxes can be obtained from dispersion relations and how it helped reducing the hadronic uncertainties. Okay, so now because, as I mentioned, we are aiming at measuring the charges at very low momentum transfers, where the complications due to hadronic structure are under control. We need to evaluate an Electroweak box at a 0 momentum transfer. So this is enough for our goal. So now for instance, taken as an example, the gamma W box here depicted on the top. This blob below represents the generalized Compton tensor. So this T gamma W mu nu that carries all the information about the hadronic structure. And this is just a loop expression that is very compact. A similar expression also can be written down for the gamma Z box. So now this generalized Compton tensor, once you incorporate all the symmetries and consider only the spin independent part, which basically is the prerequisite for the precision test, because the spin is affected by strong interaction. So there are only 3 structures that are possible here, and now to evaluate this loop, we need to know the forward Compton amplitudes T1, T2, and T3. Now, the starting point for dispersion relation formulation is we assume that they are analytical functions inside the contour in the complex plane of energy nu. And all we need to know is the singularities. These singularities, according to the general knowledge that we have also through the diagrammatic techniques, the Feynman diagrams, is that those singularities are either poles when a single particle is propagated in the inside this blob, or cuts where you have multi-particle continua. So now the nice thing is that for the forward dispersion relation, only analyticity in the energy is needed. Well, also in Q squared, but the analyticity is required in nu only. If we were to look at a finite momentum transfer, then we would have to also require analyticity in T, and this is where things would become complicated. Okay, so now to obtain the input into the loop calculation, we take a step back and first determine the imaginary parts of those amplitudes T1, T2, and T3, and those through optical theorem are related to structure functions. Now, structure functions are generally data, but not always. So for the case of gamma gamma, for instance, yes, these are the electromagnetic inclusive structure functions or total photoabsorption cross sections. For gamma z, those are also directly accessible experimentally, but doesn't mean that they exist. For the gamma w, the structure functions are really not data, because the initial and final state are not the same, and so one needs to deduce them somehow from the data. Okay, so this is just a formal definition of what the corrections, these box corrections are, how they are defined. And so now, again, so we know the analytical structure of our amplitude, and now we just need to combine together the left hand and right hand singularities. So in general, they can come either with plus or minus sign, but the situation is slightly different for the gamma z and gamma w, because again, so for gamma z, it's the same initial and final state, and so the amplitudes have definite crossing. So it's either plus or minus. For gamma w, because there is a mismatch between the initial and final state, one has a mixed crossing behavior, but one can isolate the exact crossing, well, the well-defined crossing amplitudes by decomposing the photon field into isospin 0 and isospin 1 components. Okay, then another consideration is what are the relevant scales that we need to be careful about here in this calculation. So now talking about the gamma W box, well, so the here this is essentially all the scales matter, all the way from the electron mass to the weak boson scale. Now, the way the overall radiative correction framework is set up is that everything that is sensitive to the electron mass is taken out, and so those are the Coulomb corrections, the soft photon emission and such, and those are calculated separately. So then one other relevant scale is the so-called Q value, or the maximal value of the electron energy in a given decay, and those range from 1 to roughly 10 MeV, depending on, so starting from the neutron decay and going to the heaviest super loud decay that is relevant here. So then, in principle, we have also the nuclear scales that lie roughly about 1030 MeV. The hadronic scale is an order of magnitude higher, and then the weak boson scale is very much higher again. Okay, so now the electron carries the energy that lies below this Q value, so it lies somewhere here. And so the scales that are relevant here are just these ones. So for instance, at most the nuclear scale, but clearly the hadronic scale is already would bring us to 10 to minus 5. So it is not relevant, and therefore we can conclude that only the leading behavior is sufficient, so either constant or linear in energy. Now for the parity violating electron scattering with electron energies between 100 MeV and 12 GeV, it is clear that the situation is different. So all the scales will contribute, and so the full energy dependence will be necessary. Okay, so now this is just a shortcut to the final result. So you can just perform the integration and express your boxes as functions of energy. So here electron energy E here as a double integral over Q squared and energy nu over the structure function. So now if you just look at the well, here it's 1 over E, but trust me, it is actually an even function of energy. Then this guy is actually odd function of energy, although it's not. It's also not obvious here. And here I keep the full energy dependence. Now for the gamma W box, there is a piece that is even in energy, and here I only quote the result with the leading constant energy dependence, and then the odd piece that depends on you see that they depend on two different isospin channels, and this is the linear part. So now interestingly, back in the 80s, but also all the way up until 2018, only the exact zero energy limit has been employed for the beta decays analysis, and until 2009, only this first term has been accounted for, and also at zero energy, by the way, for parity violating electron scattering. Okay, so then if you have input to your dispersion integral, so you need to model somehow the data. So here, this is the gamma Z box, and probably Peter Blandon will tell more about how this is done technically. But what was found is that there is a very steep energy dependence. So here, this is in units of 10 to minus 3. So you see that by the time you get to the Q weak energy of 1.165, it is already 5-6 times 10 to minus 3. And if you compare it to the reference value, the value of the proton weak charge, which is 0.07, you see that it is a huge effect. So this energy dependence is something like 7% of the tree level. So you see that it is extremely important to include it, and here this importance is reflected in this long publication list on the subject. So also you see that because of this strong energy dependence, the lower you go in energy, the less you are sensitive to possible uncertainties associated with this correction. And that was the main motivation for performing a lower energy experiment in mines. Okay, now how does one actually tame the uncertainties? So here I will mostly concentrate on the gamma W box, but there will be also some consequences for the gamma Z. Now, so again, for the gamma W box, the first step would be to just compute the box at zero energy, zero momentum transfer. So then only this even piece survives. And then it is informative to actually rewrite this loop integral in terms of the Nachman moment of the structure function F3. So here, this is just a mathematical definition. It is the way to include the target mass corrections in the model independent way. And so then in terms of this well-defined mathematical object M3, it's just an integral over Q squared. Now, to evaluate this integral, so again, we need to disperse our knowledge about the hadronic structure in two variables, the energy nu, or the mass of the hadronic intermediate state W, and in Q squared. So now going along this this axis, the x-axis here, you scan all the possible intermediate states that can be produced, and going in Q squared along the y scale here, you scan the dominant physics pictures, because all of these contributions are present in principle, but not all of them need to be kept, because another picture takes over. As for instance, at high Q squared, it is much more economical to use perturbative QCD description than specifically hadronic, and so on. Okay, so now to evaluate the dispersion integral, you need the input. So as I said, the gamma W structure functions are not data themselves, but by isospin symmetry, you can relate the isoscalar photon to isovector W boson. So and there we can rely on the data in neutrino and antineutrino inclusive scattering. And there, exactly the structure function of 3 has been studied extensively in the framework of Gross, Level, and Smith sum rule that states that the Mellin moment of the structure function F3 is simply related to the number of the valence quarks. So it's just 3. So here, these are world data on this on the Nachman moment of for the charge current. So you see, it is asymptotically approaches the value of 3, but it is not it's pretty slow actually. And so here you see this is the hadronic range, where unfortunately the data are scarce and not very high quality. However, so if you just compare even this poor data with what can be deduced from the description of the model that Marciano and Sirling used to compute the gamma W box, you see that there is certainly a missing strength here in this region. So instead, the blue line corresponds to our fit to this data. Well, this plot I know is slightly misleading because well, obviously this data alone cannot give you this this quality of the fit, but there is more that we know that cannot be, however, plotted on this in this plot. So anyways, then once you determine this this object here, you can use isospin symmetry to rotate it back to the one you need, the Nachman moment for gamma W. And so here again, so this is our prediction for the, so this is exactly the integrand of the gamma W box. This would be the parameterization used by Marciano and Selin. So you see that there is also a discontinuity here at the matching point. Anyways, the new evaluation led to a significant shift in the value of the gamma W box, and also a reduction of the uncertainty. So the reduction of the uncertainty was due to this the use of this data. Now, obviously, the quality of the data is suspicious, and so we decided to check it with a lattice QCD calculation. So now, unfortunately, to access it directly on a physical nucleon at physical pion mass is challenging, but there are two groups or three groups already working on that. And so the first calculation was performed on a pion. Just it is essentially the same object. So this time order product of two currents, but now the initial and final state was taken as pion and not nucleon. So maybe I'll skip these details. So essentially here you can see the so different variants of the lattice, and then doing the continuum extrapolation, you get the sense of the uncertainty. Here also is shown the perturbative QCD prediction, so that is a for loop prediction from from QCD. And so you see that already around 2 GeV squared, there is a very good matching on 2P QCD, and this is how we organize our integral. So we use PQCD above 2 GeV squared and the lattice below. So already for the radiative corrections to the semi-leptonic pion decay, it is a 1 order of magnitude reduction in the uncertainty. So this is the KPT estimate, and this is the new result. Okay, so now we need to relate this calculation to the gamma W box on the neutron, and here our decomposition into leading contributions for given Q squared really helped. It gave us the insight into what kind of physics we are dealing with, and it turned out that the only contribution that is really dominating in the, well, around Q squared of 1 GeV squared and above, slightly above, is Reggie exchanges. And the Q squared dependence is described by the vector dominance model to some extent, but we did not rely to VDM entirely. And so then it turns out that in Reggie theory, this contribution on the pion and on the nucleon are exactly related by the scaling, the Reggie factorization theorem. This theorem has been checked for purely hadronic reactions, pi scattering, pi n scattering, and n scattering. And so it is well established. So what we did, we used on one hand the lattice input, and on the other hand a body of hadronic data to reduce the result for the for the gamma W box on the neutron. And it was pretty amazing to see that the new lattice prediction and the result of our fit, they agree very, very well. So here, this is the numerical evidence for that. And so now it can be, we can state that the CKM unitarity violation at 3 sigma level is very well established, because beyond our calculation here, so also it is useful to introduce this correction delta RV. Also, 2 other groups qualitatively confirmed our findings. So this is back to the status. So right now we are evidencing the deficit in CKM unitarity with possible beyond the standard model explanations, which, however, need to be explored. Now, let me just briefly mention the situation on the nuclei. So now, the best extraction of VUD, in fact, is obtained with nuclear decays. So now, what kind of nuclear effects one can expect? So first of all, because we need the structure functions to evaluate those integrals, it is known that the free nucleon structure functions are not do not remain intact once the nucleons are embedded in nuclei. So in particular, the low energy part is really modified qualitatively. So instead of just the elastic peak on the free nucleon, so you have just an absorption of a virtual photon without exciting the resonance or producing particles. Now, in a nucleus, it's all this rich structure that appears. So there could be still elastic peak, but then also some low-lying discrete nuclear states and quasi-elastic peak. So it's this elastic peak broadened by the Fermi motion. But also at high energies, the spectrum is modified, and it has been studied in real photoabsorption. For instance, so here one studied the effective number of nucleons, and here you see that depending on whether you are looking at a light or heavy nucleus, this shadowing effect, so the fact that you see less active nucleons than there are, is clearly more visible. Also, at medium q squared, one observes the EMC effect, where there are nuclear modifications, but at asymptotic q squared, one expects to recover the operator product expansion. So now, at present, it is only this low energy part of the spectrum and the modification of the boxes due to that has been explored. All the rest is still things to do. So now, to understand how VUD is obtained here is, so we need, this is VUD as obtained from the super loud nuclear decays. So here are the very precisely known couplings. Then in the denominator, one has a combination of the experimental information and radiative corrections, and this is a universal correction that is the same for all nuclear decays. So now this is just to remind you what this delta RV is. It's a purely short range correction that is certainly is insensitive to hadronic structure plus the gamma W box. Okay, now what is measured is this so-called FT value. So it's the phase space and the branching ratio times the half-life given decay. But then, because these FT values are not the same for different decays, it is understood that there are corrections that are also, some of them are also specific for a given decay. And so one absorbs those corrections in such a way that one defines this large FT value, the modified statistical rate function, where all the other corrections are that are process specific are factorized out. So now, okay, so again, this is the structure. So this FT is everything that is experimental. Then delta R prime is QED beyond Coulomb distortion. Then there is isospin breaking, and finally this is the nuclear modification of the gamma W box. Yeah, and so here this is it seems to be trivial, but this is the first time that a rigorous definition of what delta NS is was obtained. So you just need to compute the gamma W box on the nucleus and subtract the result on the free nucleon. So, and the reason why it is important that this definition is now in place is because historically the delta RV was calculated by one method and the delta NS by another.
Hey, Mikhail?
Yes,
yes.
yes.
We've 3 or 4 minutes left, just so you know.
Yeah.
Okay, thank you.
Thank you. Okay, so now we have an explicit expression for delta NS in the dispersion relation framework, and we can compare to the previous predictions. So now the Hardy and Towner from 1994 until 2021 have been essentially the only reference for this FT values and VUD extraction from nuclear decays. So here this number and the uncertainty thereof is really the reason why super loud decays were giving us such a precise value of VUD. And so their old estimate was some old-fashioned kind of estimate with the nuclear quenching of spin operators, and that represents this first term, and the second term was completely neglected. Now with the new framework we can directly compute, at least in the model. So in this case it is a free Fermi model, and we observe two effects that although cancel each other, but they're huge. Well, if you compare it to the uncertainty of the old estimate, it is 2 sigma. And so therefore a conservative uncertainty estimate for the nuclear structure is now tripled compared to the previous. But this I need to stress that this is only an exploratory calculation. So to get this in a better shape, we started new collaborations. So with the Triumph group to compute this particular decay as the first application. They operate in a no-core shell model. On the other hand, the St. Louis group, Pastor and King, they work in a very different ab initio method, Green's function Monte Carlo. So soon we expect results. But again, so no calculation exists as of now for the high energy nuclear effects such as shadowing, AMC, and so on. And also the question of how does this shadowing match to OPE at high Q squared is another question to be answered. And yeah, so essentially the questions to be answered is how important this effect is for VUD, how important it is for nuclear weak charges and radii, probably not so, important because just the precision is much lower, but there is work in progress, and so stay tuned, please. And I just leave here my conclusions for you to read, and thank you for your attention.